Welcome to my math seminar on graph theory and linear algebra, analyzing network security. Many thanks to my advisor, Dr. Burke. So, we're looking at graph theory. Here's some graphs, you've probably seen in pre-calculus, college algebra, and calculus. Nice continuous graphs, but those aren't what we're looking at. We're going to be looking at these types of graphs today. Now, what are those? These are graphs that are defined by vertices and nodes, a vertex and a node. So this here, V is a node, U is a node, Z is a node, and the lines between them are edges. Now, you're going to ask now, what do they represent? Now, the vertices and the edges could be water reservoirs and canals. They could be airports and flights, or power plants and electrical lines, buildings and roads, computers, or Ethernet cables. Really, anything that can be visualized as components and relationships between them could possibly be represented by a graph. So these are very important in the modern world, as we have many very interconnected systems like this, a lot of money wrapped up in this. So we'll now ask the question, what if a pipe collapses? Flights cancel, a road is blocked, a power plant goes down, a cable is cut. How will the system perform? We need linear algebra. Oh yeah. First, we'll go over some fun graphs that we won't be considering. Multigraphs would be a graph with multiple edges between nodes. So see, this first graph has two edges between C and D, so it's a multigraph. Pseudographs are graphs with self-loops. So this loop C here has a loop to itself, so it's called a pseudograph as well. We won't be considering those. Directed graphs here are where we conceptualize as the edge, the relationship between each node is only being one way. Or there would be weighted graphs where there's an associated cost with each edge. We won't be considering any of these. We'll be looking at more simple graphs. So, things we can just learn from the graph itself. Binary connectivity. So this is rather simple metric. It's just saying, is there a path from every vertex to every other vertex? So if X is connected, there is such. So this graph is connected from any vertex on this graph, you could get to any other vertex. So this is rather simple metric. We could also talk about vertex connectivity, which is the minimum number of vertices needed to be removed to disconnect the graph. So if we look here at this graph X, if we removed G, we would have F here off by itself, and Z, U, and V off by itself, and so the graph would be disconnected. And so the vertex connectivity of X is 1. Obviously, if you get much larger graphs to actually represent really big systems in the world, it'd be harder to calculate this. Or you could think about edge connectivity as the minimum number of edges needed to be removed to disconnect the graph. So if we think here of the edge between G and F, if we remove this edge, the graph would again become disconnected from F, between F and G, U, V, and Z. There'd be a disconnected graph, so there would not be a pathway between every node and every other node. So another metric we can talk about is the diameter of the graph. So the diameter is the longest path of the shortest paths between all pairs of nodes. So for X here, that number is 3, because the distance from F to V, if you take the fastest path from F to V, it's 3 edges. So F, G, Z, V gets there in 3, F, G, U, V would also get there in 3. But say you took F, G, U, Z, V, that would take 4, but that's not the shortest path, so that doesn't count for a calculation of diameter. So diameter really means, if more simple terms we wanted to describe it, is what is the worst case scenario if you had to go from one random node to another. And so the worst case scenario if you had to go from one node to another would be 3 for this graph. And so the lower that number is, the more strongly connected a graph is, because it's easier to get between all the nodes faster. Your worst case scenario is lower if the diameter is lower. But now we obviously, point of the seminar is to look at how we represent graphs using linear algebra. So we'll look first at representing graphs by the adjacency matrix. The adjacency matrix we create by indexing rows and columns by all the nodes of the graph, vertices of the graph. So here you see U, V, Z, G, and F along the rows and the columns. Index the graph. And every entry in the graph is a 1 if there's an edge between the corresponding vertices. So V and U has a 1. because there's an edge between them, and a 0 otherwise. So you'll notice the diagonal will always be all zeros because we're not looking at pseudographs that have self-loops, so UU is necessarily 0 because there's not a edge between U and U, so the diagonal is all zeros. So if we look at one thing that we can learn from just the adjacency matrix is the spectral radius. So the spectral radius is defined as the largest eigenvalue, lambda, of the adjacency matrix A. So the spectral radius is related to the number of paths and loops, and so the higher the spectral radius, the more strongly the graph will be connected. We could get into the weeds of why that is, but we're going to be looking more closely at an example later on, so we're just going to say that the spectral radius is the highest eigenvalue, and that is, the higher that is, the more strongly connected the graph is. So if we remember our eigenvalues and eigenvectors, an eigenvector x of the matrix A is a vector such that matrix A times that vector x results in just scaling that eigenvector x by some lambda scalar. That lambda we call an eigenvalue. And so to solve for the eigenvalues, we would write, we would algebraically simplify it as A minus lambda times I being the identity matrix, since lambda is just a scalar, so we can't subtract it from A without making it into a matrix. And so then that then equals 0. And so we have this as a visual representation of the graph, the matrix here of A minus lambda I. And so then to find the different eigenvalues, we would take its determinant. We could talk about why that is. It has to do with the infamous invertible matrix theorem, why the determinant gives you the different eigenvalues. But it does, and so what you do here is you take the determinant of this, and that yields a characteristic polynomial of the different lambdas, and the roots of that will be your eigenvalues. And so we have here what we call the spectrum of lambda, which is your different eigenvalues. And so your highest one here is 2.641. And so since the highest lambda is spectral radius, it's 2.641. The higher that is, the more strongly your graph will be connected. As we are trying to look forward ahead, we'll be talking about the Laplacian matrix, but first we have to know about the diagonal matrix. The diagonal matrix D is the matrix where each of the vertices elements on the diagonal is the number of edges connected to it. And so everything else is 1. So this is a rather simple representation of the matrix. So U has 3 edges on it, and so it's 3 on the diagonal. V has 2. And Z has 3, G has 3, F has 1, and so everything else is going to be represented by zeros. And so that takes us to the Laplacian matrix. So the Laplacian matrix that we'll be looking at most chiefly today is defined as the diagonal matrix minus the adjacency matrix. And so here, if you think about that, the diagonal, since the diagonal of the adjacency matrix is always zeros because there's no self-loops, the diagonal is always the degree of each node, meaning how many edges are in each node, and everything else is a -1 if there is an edge between the corresponding nodes, or it is 0 otherwise. So we're going to be looking at today Kirchhoff's matrix tree theorem as an evaluation of graph vulnerability, and Kirchhoff's matrix tree theorem is that the cofactors of the Laplacian matrix are all equal and are equal to the number of spanning trees in the corresponding graph. Now, that's a bunch of fancy words, but what do they mean? Now, if you remember cofactors, a cofactor of a matrix M is the determinant of the submatrix M obtained by deleting a row and a column from M. And so there are lots of different cofactors of M, but see, if we deleted this row here, this column here, and this row, we then get this resulting matrix, and if we took that determinant, that would be a cofactor of the matrix M. So obviously you could delete a lot of different rows and columns and get a lot of different cofactors. But a cofactor is simply that. You delete a row and a column, and you take its determinant. And then we also have to talk about spanning trees, the other thing in the definition. So trees are connected and acyclic graphs, and spanning trees would be subgraphs within a graph that span all the vertices within the graph, also without cycles. And so if we were to look here at some examples, we have our graph of X that we'll be looking at today, and it has cycles. So you could go from V to Z to U back to V without traversing over the same edge. That's what we would define as a cycle. So it has cycles. It's not a tree. This here is an example of a tree where you can only get back to different vertices by traveling over the same edge. And so here would be an example of a spanning tree of the graph of X. So this spans all the different vertices of X, but it does so as a tree. And so as we'll be looking at Kirchhoff, well, I guess not all trees don't have cycles. So now as we're looking at Kirchhoff's matrix tree theorem, we're saying that the cofactors, if we delete a row and a column from the Laplacian matrix and take its determinant, they're all going to be the same value, and that will be equal to the number of spanning trees in the corresponding graph. That's not fairly intuitive. Why is that the case? We might want to prove that. So we're going to be looking at proving this. So we're going to try and prove Kirchhoff's matrix tree theorem by induction. And so induction works as you have a base case and then proving that k implies it's true for k plus 1. And so our base case, if there was any graph of n vertices and 0 edges, it would have a matrix, zero matrix, Laplacian matrix. And so the cofactors of a zero matrix will all necessarily be 0, and there will also be 0 spanning trees in the graph because there's no edges. And so it's a very simple base case where it's 0 equals 0 for Kirchhoff's matrix tree theorem. But for the bulk and the substance of the proof, we need to prove that the theorem being true for k number of edges implies that it's true for k plus 1 edges. So we'll be looking at this. To do this, we'll be looking at the deletion and contraction of edges. So we're going to define up here E equal to the edge between V and U. We're going to be talking about this in the abstract, but there will be visuals for the graph that we've been looking at. So this is just any graph with an edge E on it between V of two vertices V and U will be what we'll be considering. And so if you have X here, if you delete E with this notation X backslash E, you simply remove E from the graph. But if you contract E, you contract U onto V here is how we'll define the edge VU being contracted. And so V and U become one node, and it'll take the name V, it'll keep the name V. And so this could create multiple edges, but we're not going to be considering multiple edges in the original graph, just if it happens in the contraction of the graph, that will be okay. And so here we have X contract E and X delete E as two different graphs that have one less edge than our original graph, and so this will be used to do our k and k plus 1 of our induction. And so if we're going to prove Kirchhoff's theorem, we're going to start by thinking about how all spanning trees of X either do or do not contain E. So that's just a necessary part of the logic, that a spanning tree must contain E or it must not. And so all the spanning trees that do not contain E are also going to be spanning trees of the deletion of E. So if we think here, you delete E, this graph here will have no spanning trees from X that contain D, but it will contain all the ones that don't contain E. And then we'll also think that all the spanning trees of X either do or do not contain E. But if we were to do the math, we won't do it for the sake of time here, but we'll say that there's a one-to-one relationship between spanning trees containing E and the spanning trees of X contract E. So this graph here has as many spanning trees as X does that do contain E. And so that helps us write the first equation that we have here, that the total number of spanning trees we'll define as T of X of the graph X is equal to the number of spanning trees in the graph with the E deleted and with E contracted. So T of X equals T of X delete E plus T of X contract E. So now, a little more notation before we get into a lot more of the algebra of the proof. Here we'll define V of X as the vertex set of the graph X. And we'll let L of X be the Laplacian matrix of the graph X. And then we'll let L of X bracket U and any other vertices be the Laplacian matrix of the graph X with the U and whatever else rows and columns deleted. So you'll see here if you take L of X delete U, that deletes this first row and this first column and first row. But if you delete U and V, you delete the next ones, and you could use this notation to delete any row and column from our graph that's in our matrix that's indexed by the vertices of the graph. And so now we'll look at the notated version of Kirchhoff's theorem is that the total number of spanning trees is equal to the determinant of the Laplacian matrix deleting some arbitrary node U. And so if we'll remember here, we're going to be looking at visuals that are as a concrete matrix X, but this will apply for any arbitrary Laplacian matrix with any two nodes U and V and with an edge and with more nodes. So here we'll look at the Laplacian matrix, and we'll look at the difference between the Laplacian matrix in the normal graph and the Laplacian matrix when we delete E. There are four things that change. The U and the V elements in the diagonal are decremented by 1, and then the UV and VU elements are both made from -1 to 0 because that edge is now gone. So those are the only things that change, but then we'll also look at if we delete U from there, 3 of those things change. Because E is defined as between U and V, if we were choosing some other node, this deletion would also move with it. So the only thing that's left is that the VV entry on the Laplacian is decremented by 1 here. And so then we could use that knowledge to write this new equation where the Laplacian matrix of x delete U is equal to the Laplacian matrix of x delete E and delete U plus this new matrix H that we'll create, which is just a matrix of equal proportions that just has 1 in the VV diagonal entry to make up for the decrementing that happens with the deletion of E. So then here we'll look at how we have to take the determinant of each side because that's part of our definition for Kirchhoff's theorem. So we take the determinant here. So to further look at this, we'll first consider just the determinant of the Laplacian of x delete E and delete U. And so if we were to take this and we were to do our cofactor expansion, the process for finding the determinant of a matrix, we would find we can define this as, because you can take the cofactor expansion of any row and column of the matrix, we could define it as this first term that is LVV, which would be this one here, delete those rows, and then take the determinant of this matrix, this cofactor of this, and we have this minus and plus all the other terms of the cofactor expansion that would be written out if we take the determinant. So we get this LVV here. And what we'll notice is that this first term is the only one that's going to have LVV in it, and when we add H to this Laplacian, it only increments LVV. And so we can write this here, where we do LVV plus 1 into our expression for the cofactor expansion, that being equal to our determinant here with the plus H in there. So we'll be able to distribute this LVV plus 1. And so when we distribute that, we get the determinant of the Laplacian deleting U and V plus this here. But this is what we said was the determinant of the Laplacian of x delete E delete V. And so that will allow us to write this now, where the determinant of the Laplacian plus H is equal to this determinant where we're deleting U and V plus the determinant where we're deleting U. And so now here, we'll plug that back into our original equation. But we'll notice that since the deletion of E affects only the columns of U and V, we can say that the determinant of the Laplacian of the regular with deleting U and V is equal to deleting the edge E. So this deletion of the edge doesn't matter because we're already deleting U and V. So this is equal to that. And then we can say here the simplified version where we don't have this delete E because it doesn't matter. So that's our next line of the algebra here. And so now we'll think about how when contracting E, we're defining V is onto U. So U is removed from the vertex set. So the vertex set, if we contract E, is equal to the vertex set originally, deleting U. And so if we look at that here, if we contract E and then delete V, this removes both U and V from the Laplacian. So now we can say this, that the Laplacian when we delete U and V is equal to the Laplacian if we contract E and delete V. So then here, we can reinsert that we've found now into our equation so that the determinant of the Laplacian deleting U is equal to the determinant of the Laplacian of x contract E delete V and the determinant of the Laplacian of x delete E and delete U. And so we're proving by induction, we assume that for this contraction and deletion that Kirchhoff's theorem is true. So we assume these things at the bottom here. And so that allows us to write that the determinant of the Laplacian delete U is equal to the total number of spanning trees in the contraction plus the total number of spanning trees in the deletion. But if we remember earlier that we discovered that the total number of spanning trees is equal to the total number of spanning trees in the deletion plus contraction, we know now that the determinant of the Laplacian of x at any arbitrary node U, deleting any arbitrary node U, is equal to the total number of spanning trees, which is our Kirchhoff's matrix tree theorem, which means that it being true for k number of edges in the deletion and contraction implies that it's true for k plus 1 number of edges. So therefore we have proved Kirchhoff's matrix tree theorem by induction. There's also an eigenvalue form of Kirchhoff's here, where we'll notice if we were to look into the maths of this, we won't do it for time's sake, but there's always going to be one eigenvalue equal to 0 in the Laplacian, and so if we take all the others that don't equal 0, multiply them together, and divide them by the number of eigenvalues, that is also the number of spanning trees in the graph of x. And so if we were to calculate it here by cofactor form, we find that the number of spanning trees is 8. And if we also find the spectrum here, multiply them together, except for the 0 that comes out, and divide it by the number of eigenvalues, we get that the total number of spanning trees is also 8 by the eigenvalue form of Kirchhoff's. And so here we have the 8 spanning trees that are in the graph of x. You won't find any others if you were to look for a spanning tree within this x. And we can calculate, for much bigger graphs, so we can't just count them, the number of spanning trees by Kirchhoff's matrix tree theorem. Here's a table from the article that sort of inspired this work, where it shows vertex connectivity, edge connectivity, diameter, spectral radius, and number of spanning trees. They go over a whole lot more of the different mathematical techniques that can be used to address the vulnerability of graphs. And so we see here that the larger value of spectral radius, the higher value of number of spanning trees, leads to stronger connectivity and then more alternate pathways for the number of spanning trees. So if you think that's a little intuitive, the number of unique sets that span the entire set of vertices is the number of spanning trees. And so there's more alternate pathways the more spanning trees you have. So if you delete an edge, there's more likely to still be a way to get where you want. And so the article goes on to talk about the most likely attacks, where the most likely attacks are that an edge goes down or that a node goes down. And then it also goes on to describe some of the ways that those are combated in the different fields that use graphs. But that is the seminar for today. Thank you very much. Here are my sources.